So here we have problem 4 of the week 2 homework. And I will work through problem A, the first part of it, and I'll leave the remaining 3 sections for the student to work through. This is real similar to problem 3 with the exception of now we are trying to add together or resolve 3 vectors, but the process is exactly the same. So we're going to break each of these 3 vectors into vertical and horizontal components, and then find the lengths of those components, and by definition, because we've said they're vertical and horizontal, we know their direction, and once we know directions and length, we can simply add them by placing them into a free body diagram. So let's think about this vector here. What's the length of this vector here? Well, we see that this is the side opposite, this is the side adjacent to the 30-degree angle. The hypotenuse of this side is 5 meters. So think about our trig functions. So, ka, toa. We're looking for something that relates opposite and hypotenuse. If we're looking for the opposite side, that's the sine function. So what we can say is the sine of 30 degrees equals the opposite side, which we're trying to find, over the hypotenuse, which is given as 5. We can just simply push this thing around then, multiply both sides by 5. 5 times sine of 30 degrees will give us the length of the side opposite. So we'll just use our calculator for that. 30, I make sure I'm in degrees mode, sine times 5 is 2.5. So what does this really tell you? Well, it tells you that the person who walked along the line C there in a kind of northeasterly direction accumulated a total northward distance of 2.5 meters. Now, we're going to start a free body diagram in the lower left corner here just to kind of stack up all of the numbers that we've come up with. So we're going to start at this point, and the first move we know about is a move up at a distance of 2.5 meters. How about the side adjacent? Well, the side adjacent, again, the angle of interest is 30 degrees, the hypotenuse is 5. We need something that relates the hypotenuse and the side adjacent, and you see here that that's the cosine function. So again, cosine 30 degrees equals the adjacent side over 5. Multiply both sides of this formula by 5. You get 5 times the cosine 30 degrees. And again, we will use our calculator. Oops. So 30, and we're in degrees mode, cosine times 5 is about 0.43. I'm sorry, 4.3 meters. And if we think about the direction of this first vector, it's to the right. So we will draw a vector down here on our free body diagram, 4.3 meters to the right. Now, the process is precisely the same for this second triangle that has a hypotenuse of b, length 7. So let's go take a look at that. So the first thing we have to do is we have to figure out this included angle. Well, the included angle is the complement to 70 degrees, which is just simply 20 degrees, because complements add to 90. Again, we have a side opposite, we have a side adjacent, and the process is the same. Sine 20 degrees equals the side opposite over the length of the hypotenuse, which is given as 7. So we'll multiply both sides by 7. 7 times the sine of 20 degrees. So 20, we're in degrees mode, sine times 7 is about 2.4. Now, if you think about the horizontal component of triangle B here, it's to the left. So we'll draw in a vector this way, 2.4 meters. And the vertical component, calculated using a similar procedure. I'm sorry, this 2.4 does not represent the horizontal distance. It represents the vertical distance, and it's upward. So let's draw that in there. I drew that previous one in the wrong place. 2.4 meters. That's the vertical component because sine relates the opposite side. So we'll just go ahead and erase. We'll just go ahead and erase this vector over here. We don't need it yet. Okay. Now let's look on that horizontal component. Horizontal component is the adjacent side, so we're going to use the cosine function. Cosine 20 degrees equals the adjacent side divided by 7, multiplying both sides by 7. 7 times cosine of 20 degrees is going to equal the length of that adjacent side, which will be the horizontal component here. So we'll clear out of this. 20 degrees, we're in degree mode, cosine times 7 equals about 6.6. Now, if you think about the representation of that, that arrow is to the left. You could think about the number as being negative 6.6 if you wanted to, because the force is to the left. Or as long as we keep track of directions of things, simply draw it in and use the direction of the vector to tell you how things are. Okay. The remaining triangle, triangle A, has an included angle of 55 degrees, which is given in the problem, and it has a hypotenuse length here of 4 meters. So again, it has a side opposite, which is going to represent the vertical component, and a side adjacent, which represents the horizontal component. So what do we know? Well, sine of 55 degrees equals opposite over hypotenuse. The hypotenuse length is given as 4 in the problem, so multiply both sides by 4. 4 times the sine of 55 degrees gives you the length of the vertical component of this vector. So 55, we're in degree mode, use the sine key, times the length of the hypotenuse, which is 4. So the vertical component is about 3.28. We'll call it 3.3 just to keep the numbers easy to work with. Now if you look at triangle A, vector A, its magnitude, its vertical magnitude is downward. So we're going to put that in that direction and label it 3.4 meters. I'm sorry, we're going to label it 3.3 meters. 3.3 meters. The last piece to figure out is the horizontal component of vector A, and that we can use the cosine function for because the horizontal component is adjacent to the angle. So cosine equals adjacent over the length of the hypotenuse, which is 4. We multiply both sides by 4 times the cosine 55 degrees, and that will give us the horizontal component. And then multiply that times the length of the hypotenuse, which is given as 4, and we see that that's about 2.3, and it's 2.3 to the left for triangle A, or for vector A. So now what we need to do is get all of these horizontal and vertical components into single unit vectors. So if you look at the vertical addition is going to look like 2.4 plus 2.5 minus 3.3. Now, if the sum of these three numbers is negative, that would mean that the magnitude of the resulting vector is going to be downward. If it's positive, it would mean that it's going to be upward. And just looking at the numbers, we can tell that it's going to be upward. So 2.4 plus 2.5 minus 3.3 is an upward component of about 1.6. And again, the unit here is meters. So I'm going to draw a new free body diagram, and this new free body diagram is going to have a point, and from that point is going to be projecting a vector 1.6 meters upward. The horizontal component is going to be added as follows. We have 4.3 meters to the right, which is a positive number, and then 6.6 to the left, which is a negative number, and 2.3 to the left, which is also a negative number. And we're going to sum those three terms. So 4.3 minus 6.6 minus 2.3. And we find that we get a magnitude of negative 4.6, which in this coordinate system means an arrow pointing to the left, 4.6 meters. Now we're not totally finished here because we still need to get these two components resolved back into a single vector. So remember the process for that is we're going to slide those head to tail. So I'm going to redraw my 1.6 meter vector here. I'm going to redraw my 4.6 meter vector here. And I'm going to figure out the length of this resultant. Well, remember that by definition this corner is 90 degrees because we said the 1.6 meter vector was straight vertical and the 4.6 meter vector was straight horizontal. So this is, middle school math at this point. 1.6 squared plus 4.6 squared equals side c squared. That's the Pythagorean theorem. How do you get to just c? Well, we take the square root of both sides. So if we root both sides, we have to complete the sum, the squaring and the sum inside first. So 1.6 squared plus 4.6 squared equals, and then we're going to take the square root, which we do by raising to the 1/2 power. So about 4.9. So the length of this resultant vector is about 4.9 meters. Now, the question is, what is the angle? Well, remember that angle is always given from 0 degrees, which is straight to the right in the Cartesian plane. So, well, what do we know? We know that the angle of this vector plus the included angle add to 180. So the angle, the heading of this vector is going to equal this angle we'll call theta subtracted from 180. Well, how do we find theta? We want to relate the opposite and the adjacent. So that's going to require the tangent function. So tangent theta equals 1.6 over 4.6. Now the problem with that is that the tangent, you can think of a function as a machine. The tangent machine is a machine that you drop an angle in one side and you get a ratio of sides out the other. But we need just the opposite. We know the ratio of the sides and we need the angle. So we have to use the inverse function. We have to use the anti-tangent machine, or what we'd call arctangent. So the arctangent of 1.6 over 4.6 is going to equal angle theta.